So we have seen that by looking at the Taylor expansion of a two-dimensional function, a function with two variables, we can tell a lot of things about the stationary points. In particular, by looking at the first order term of the Taylor expansion, which is the one that involves the first order partial derivatives, we can tell which points are stationary points. So stationary points are those in which the first order term is equal to 0, which also means that the two first order partial derivatives are both equal to 0 simultaneously. So that's in order to know where the points are. But another question is how to classify the points. And a way of classifying the points is by looking at the second order term in the Taylor expansion. This term includes the second order partial derivatives. So, for example, if this second order term is negative, we know this is a local maxima, and if this second order term is positive, then we know we're in a local minimum. Okay? So far, this is all remarkably similar to the one-dimensional case, right? The stationary points are those in which the first order derivative is 0, and then the sign of the second order derivative tells you if you are in a local minimum or in a local maximum. So far, it's exactly the same. However, in two dimensions, things can become a bit tricky. In particular, how can you know, for example, if the second order term is negative in all directions? So how can you tell if this term is always negative? So one might naively assume the following, and this is wrong, but maybe you think, okay, I calculate the 4 second order partial derivatives, and if they are all negative, then this term must always be negative. So this is very tempting, but this is wrong. And to show you why, I'm going to show you an example. So in this example, the 3 second order partial derivatives are going to be negative, and yet this term is going to be positive under certain circumstances. So let's have a look. So consider this function. This is a very simple function, f of xy equals 1 minus 3x squared minus 8xy minus 3y squared. So first step, we calculate the first order partial derivatives. So here they are calculated, okay? So we equate them to 0 in order to find the stationary points. So from the first equation, we find that x equals minus 8/6 of y, and from the second equation, we find that x equals minus 6/8 of y. So these two equations must be solved simultaneously, and the only solution to these two equations is that both x and y equal 0. And therefore, this is going to be a stationary point for this particular function, okay? So at x and y equals 0, we have a stationary point in this function. So let's try to classify it. So in order to classify it, we need to look at the second order partial derivatives. So we calculate the 4 second order partial derivatives, which is very easy to do because the first order answers are very simple. So the derivatives actually turn out to be constants. Minus 6, minus 6, minus 8, and minus 8. They are all negative, okay? And therefore, the second order term in the Taylor expansion, which I copied here for ease, okay, this is the same term that I was using up here, but I copied it here. So you can see that all of the terms that involve the partial derivatives, they are negative, okay? So therefore, you might think that if these three things are negative, then the whole term is going to be negative. So let's check that. So I'm going to substitute each of the partial derivatives to their appropriate location. So this is the second order partial derivative with respect to x is minus 6, so I substitute minus 6 here. Then the second order partial derivative with respect to y is also minus 6, so I substitute minus 6 here. And the mixed partial derivative is minus 8, so I substitute minus 8 here. And I arrive at this. Okay, so this is the equation for the second order correction. And you can see that this second order correction depends on delta x and delta y. And now look at this. If I choose delta x equals 1 and delta y equals minus 1, you substitute delta x and delta y, and you find that the second order correction equals 2. It is positive. Okay? However, if you choose, for example, delta x and delta y equal 1 and 0, so I substitute delta x equals 1 and delta y is 0, so these two terms go away, so we get minus 3. Which means that for different values of delta x and delta y, we are getting different signs in the second order term of the Taylor expansion. How is this possible? What is going on? This is a plot of the function. Okay, so here I'm showing the x-axis, the y-axis, and then in the z direction I'm plotting the function. So that's why we have this surface. Okay. So now we choose a point in the xy plane corresponding to this x and this y. Okay. In this case, this is the origin. We know that when x equals 0 and y equals 0, we have this point 0, 0. And then the function at this point is given by this value, which is the height of this surface. Yeah. And we know that this is a stationary point. And indeed, we see that this is a saddle point. However, it is a very tricky saddle point, because if you forget about the variations in y, so we fix y to be y0, and we change x, then we move along this red line. And this red line right here, is a maximum. It's a local maximum, right? On the other hand, if we fix x equals 0 and we only change y, we are moving along this other red line. And this red line is also a local maximum. So that's why the partial derivatives with respect to x and with respect to y, the second order, they are both negative. However, there are some directions, for example, this direction or this direction, in which the function grows instead of becoming smaller. Okay, so that's why when we moved in this direction, delta x equals 1, delta y equals minus 1, which means we are moving delta x equal to 1, and we are moving delta y equal to minus 1. So when we move in that direction, we are moving in this direction here. And you see that indeed we are rising, because the second order partial derivative is positive. It's equal to 2 in that direction. Okay? So depending on the direction, in some directions the second order partial derivative is negative, but in other direction it is positive. Okay? So now you might ask, okay, so if the way to check if this expression is always negative is not to check the individual partial derivatives, how can we be sure that this expression is always negative or always positive? Fortunately, there is a very easy way to figuring this out, which I'm going to explain in the next video. So thanks for watching.